We start building our predictive model in this first screen. Point the model at the database and tables that contain the event and monitored condition data. Those tables now appear in the tree view on the left. Now I enter the project's general information. CBM model. That would be the name of the asset, component, or failure mode whose failure behavior we wish to model. We are working with the simplest template of a single failure mode, but we could be using a complex itemed template, which models the more general case of two or more failure modes in a single asset. I'll build the model. A new entry called C Inspections appears on the tree. It combines in a single table the events with the condition monitored data leading up to those events. A learning algorithm will parse each row of this table, iteratively build a hazard rate equation. It outputs a report that shows the parameters of the hazard equation as estimated by the algorithm. We have three parameters, one for iron, lead, and the shape parameter, also known as beta in the equation. These parameters indicate the respective amount of influence each condition indicator has on failure probability. The final step in the algorithm, a third computation to optimize replacement decisions in keeping with the user's cost and availability objectives. We can consider cost or availability or a combination of cost and availability. We'll choose the simplest optimization, cost. The user supplies relative cost estimates for replacement and failure. Replacement cost, say $1,200. Failure cost, say $6,000. That gives us a graph of the average cost of ownership as a function of risk. We can look at the report to understand the optimization. It tells us that the optimal policy will reduce long-term costs by 75%. It's time to export the model to the real world where we put it to work. And here is a basic version of Appendix C as described in your request document, providing the optimal replacement times for each unit of the fleet. This version of Appendix C tells us pretty much everything the asset manager needs to know, including the optimal replacement recommendation, failure predictions, and confidence intervals. If we go back to the decision agent report, we can drill down to any unit and get all of the information we need to justify a replacement. The optimal decision graph, failure probability in the next observation interval, the conditional probability of failure, the conditional density function, and a table of failure probabilities within various future time windows. Thank you.
The maintenance technician receives a call from operations, indicating that the shovel arm does not lift. He arrives and realizes that the lift command is not getting to the front attachment. The fault code on the operator's display indicates a communication error between the control lever and the control panel. Upon examination, the tech notices that the control lever is damaged. He replaces the defective part and the shovel is brought back into service. Let us assume the role of the technician and complete the work order form
using the Mesh Event Capture user interface.
As the technician, having executed the job,
I'll log into the Mesh Event Capture app.
This is a table of open work orders. I'll filter on my work order code
and hit the Asset Hierarchy icon.
I can search for the failure mode by drilling down into the system, component, function, and so on, but an easier way would be to enter a few characters into the search box. Let's try lever and hit the search button. The tree expands, spotlighting the paths to all failure modes containing the search string lever. There are several hits, but we quickly recognize the failure mode we're looking for. Just to make sure, as the technician, I'll right-click it and select View. I'll examine the effects, consequences, and current mitigation plan. Satisfied that this is the failure mode that has failed, I'll hit Select and Functional Failure because my company has incurred the operational consequences of this failure mode.
This innovative yet simple event capture procedure will ensure that a predictive replacement algorithm will benefit from a consistent learning set. Thank you.
This is a quick overview of the Faraday Predictive Condition Monitoring System, which monitors the entire machine just by measuring voltage and current being drawn by the motor. Firstly, the overall condition of the machine present in the short term, 1 month ahead, and predicted 3 months ahead is shown as green, okay, but there's a red light for electrical condition, the present electrical condition. That red light is driven because one, at least, of these 4 parameters on the right hand side that relate to electricity supply is red, in this case voltage THD, total harmonic distortion. And if we want to know more about the details of there, we can turn on this panel showing the detailed measurements taken, and in this case voltage total harmonic distortion is 2.66%. The machine condition is shown as green, present and short and long term predictions, because all of these parameters at the left hand side, the ones with the brown bars, are green. The machine has the capability of detecting maybe 40 different failure modes. It only displays those that are relevant to this machine. We can see they're all okay, both at present and in the future. Any one of these parameters, if we want to know more about it, we can click on the bar. It's selected up here, provides us various information, and we can tell you all about that particular problem. In this case, unbalanced misalignment. What do we mean by that problem? What's the cause? What's the effect? Crucially, how and why has our system detected it? We want this to be transparent. And once you're clear what the problem is, the guidance on corrective action is normally straightforward. Where does all that information come from? It comes from measurements of current and voltage. So here, 3-phase currents, you can see they're highly distorted. If I turn on the voltages, you can see those are also highly distorted because in this case it's an inverter-driven machine. We use that to create a residual current, which we then turn into a spectrum. The system automatically identifies particular peaks on the system. You can see some are electrical, some are mechanical, some relate to the motor, some relate to the driven machine. So, and it's this that drives the condition page that we were looking at before. So that's a very quick overview of what this system does.